announcement is I don't know if, how many of you are eligible, but there's this NSF graduate fellowship. So if you are eligible, most first year and second year domestic students are eligible for this, PhDs. And so there's like an information session. Unfortunately, it coincides with this class, next class. But you can leave at like 11:30 or something. It's probably useful to go to these days because the fellowship itself is a nice thing. So, sorry. Alright, so this is just, you can search for this on the grad school webpage and you should find something, some link of this kind. And yeah, so this is good to know for most first and second year PhDs. Alright, so let's continue where we left off. Okay, so we saw the last couple of lectures, we've been looking at this paradigm called divide and conquer. Right, so divide and conquer is this general paradigm for solving problems, where you have a problem instance, you break it up in a somewhat natural way into sub-instances, and you solve these sub-problems independently of one another, and then you somehow combine the solution. Okay, so that's the general paradigm. And the important thing is that these sub-problems are all independent, right? Like you solve them totally independently of one another. Right? And we showed how to analyze such algorithms. We usually proved these things by induction. We said that you break up the problem, you assume that the sub-problems are solved correctly, and then you show that the combination steps preserves the correctness. So that's how we analyze these algorithms. And we saw a detailed example with median, with merge sort. Okay, and we also saw runtime analysis using recurrences, and we said that usually you can represent the running time of the algorithm as some function of the running time on smaller instances. Okay. And there are a bunch of homework problems on this. And the smaller instances are what you use are basically the sizes of the subproblems. So those are the smaller instances, and so your overall running time will be some function of the running time on smaller instances plus the time for this combine step and the time for this divide step. Okay, so usually the divide step is relatively cheap. Combination can be tricky. Okay, so that's how we analyze running time for divide and conquer algorithms. And this leads you to some recurrence, which is something of this kind, some expression of this kind. And then we said that there are many ways to solve this recurrence and come up with a closed form, which is some function of the kind, something like n squared, n cubed, whatever, right? So, and we saw a bunch of techniques to do that. One is this recurrence tree, and then we saw this plug and chug method where you just expand things and hope for the best, hope to see a pattern. Right? And then we said you can also guess and prove. And we said there are many other techniques, but there's no one technique that solves all. It's something that just you get used to it and you learn to recognize common patterns. So that's okay. So that's about how you solve recurrences. And last time we didn't have too much time for this, but some of you posted some questions on Piazza. So if you have more recurrences, I was actually hoping for more complicated recurrences. So feel free to still post. I will try to answer them, answer as many as I can. We were doing one recurrence which I thought of continuing today, but then I think it's better done on Piazza because I can just post the solution and you guys can read it. So we started doing this thing that looked something like E of n equals E of n minus 1 plus E of root n plus 1 or something like this. And not T of n by 2. Last time we observed that no polynomial, that this has to be bigger than any polynomial. So that's what we ended with last class. That we were trying to go via this guess and prove method, And we said that, oh, okay, let's try to guess what it can be. We said that, it cannot be polynomial. It has to be bigger than that. So it turns out that the solution to this is something like n to the log n. If you think about this better than, this is larger than any polynomial, because a polynomial is like n to the 4, n to the 5, some fixed constant. But this is like n to the power of log n, which is a function of n itself. But it's still much smaller than 2 to the n. Actually, how many of you don't see why this is much smaller than 2 to the n? Because it's may not be immediately obvious. Okay, some of you don't see. So, actually, those who do see it, why is this true?
Doesn't the power dominate and log n increases a lot slower than n does?
Right, n increases, but why is it n to the power of log n much smaller than 2 to the n?
Because power dominates, so regardless of what the base is.
So that's intuitively true. So if this were 2, I agree with you.
Okay.
But now this is m, right? So this itself is a growing function. If this were 5, I would still agree with you.
Okay.
Right? So yeah.
We can take the log of both sides.
Right. So the easiest way is to just take the log on both sides, or if you do that, then the right side becomes n, and the left side is just log n times log n, which is log squared. So, and now you can use now the log always grows much smaller than any polynomial. Alright, so that's how you see these things. Okay, but I'll give you a way of actually coming up with some formula like this. Okay, so for that, look out on the Piazza page. So one small part of homework 1 is to actually log in on Piazza. So hopefully all of you will do that. Sign up for some. Alright, so this is what we've been doing. Okay. And I also wanted to recap something we did somewhat quickly last time, which is we also looked at integer multiplication. We said that multiplying long integers is something that it's a very basic subroutine in a whole bunch of problems. And we said that if you do the naive grade school method, this gives O n squared that time. If you had n digit numbers. Then we try to see if you can do better using divide and conquer. Right? And if you did it naively, we ended up with recurrence like this. We broke the problem up into like 2 sub-problems and we tried to multiply. We ended up with a recurrence like this. And then we saw that this thing was actually no better. So even after doing all this effort, this still solves to something like T of n equals n squared. And so after that, we said, okay, so instead of doing 4 of these add operations, can you do better? And 4 of these recursive operations, can you do better? And we said that using a little bit of tricky manipulation, you can do it with just 3. And this gave rise to this other recurrence, which we said solves to something much better. And this was n to the power of log 3, which is to the base 2. And that's something like n to the 1.58. And this is much better than n squared, of course, as n grows. Right? And you can ask if you can do this much better, and it turns out this is possible. You can actually do a much more finer division, and you can actually bring this down to n to the power of 1 plus epsilon for any small epsilon. Okay, so the same rough idea. And so this is called this process. I mean, the final algorithm is called Toombs algorithm. Somehow, even though this is very much like the 1.58, it's not as popular. So you may not see this in the standard textbook. Okay, but if you look it up, you will find it. So it's called Toombs algorithm. Also, if I used to have this as a homework, so you can look up last year's homeworks. Hopefully, you guys know how to do this. How many of you know where last year's homeworks and solutions can be found? Yes, this is surprising. But I should, okay, I can add a pointer to last year's course web page, and that has homework problems and solutions. So I'm not reusing this time, so so you can actually look it up. So yeah, so I used to have this as homework problem, but since all of these are available, I won't be using this. All right, so that's integer multiplication. Okay, and actually, one of you asked me about lecture notes. I think I answered this last class. So for divide and conquer, we are just using the corresponding chapter of this Vazirani textbook. I had a link to this on the course webpage. Okay, so if you look at the course schedule on the Canvas page, you will find a link to a chapter from this book. Okay? And that basically, I mean, we are basically following things from there. So I don't have extra notes for this. For divide and conquer. And there you can find the details of this 1.58. Alright, so this is what we did. Now, yeah, so then I want to also cover this problem as one of the canonical examples of divide and conquer. This I think is a non-standard example. So let's start with this basic question. Okay. So the goal is I give you n integers that are not sorted, okay, a1 through an, and assume they're all different for now, just for simplicity. And you're given some number k, and your goal is to find the kth smallest integer in this array. Okay, you're given some unsorted array of numbers, and you want the kth smallest integer, and yeah, assume they're all distinct. Okay. So how do you do this? Okay, so the easy bound is first sort and then just find the kth small. How long does this take? First sort, then take kth small. This takes over. Okay, so the natural question is to ask, can you do better than this? Right? So, can you do better than sorting? Okay, we know that sorting cannot be done anything better than n log n. Okay, so that turns out. We will probably see the proof later, but yeah, it doesn't matter. Okay, so it turns out sorting cannot be done in general better than n log n. So, is there a way to avoid actually sorting? So, how many of you have seen an algorithm for this problem? Okay, so some of you have seen an algorithm that. So, what is the runtime of the algorithm that you've seen?
I'm trying to remember myself, but I know that
If it's the one I'm thinking of, it runs in all.
Okay, yeah, so we will see this algorithm. Okay, so it's a very simple divide and conquer algorithm. I mean, it's conceptually simple. It's the details are a bit intricate, but conceptually it's quite simple. And this is it takes time just for find. And this is surprising because it's like you're given an unsorted array, and you're asked to find the kth smallest element, and you basically can find it in time that's proportional to the amount of time it will take you to do one pass over the array, right? So, you know, you should find it surprising. Like it's just, at the same time, it's just going through the array. So, of course, it's constant. Okay. All right. So that's what we will see. And so, what is the idea? Right. So the idea is to use divide and conquer. So, how would you normally do divide and conquer in such a problem? Okay.
I think I will just divide the array into subarrays and then extract the smallest integer in those subarrays and then compare the smallest integers in each subarrays. The smallest one is going to be the smallest subarray.
So that's great for finding the smallest element, right? So what he's saying is, suppose k is equal to 1. You really want the smallest element. Now it's easy, right? You can break up the array into 2 pieces, find the smallest element of each of them, and the smaller of the 2 will be the smallest element in the whole array. So this is easy if k were equal to 1. But what about general k, right? Like suppose I ask you to find the, let's say, n over 3th smallest element, right? You can still think that maybe you will break this array up into two halves. Okay, so you have this array A. You might be able to break this into 2 pieces and say that I will find, and no, so the k prime smallest here and something else here, and maybe one of them will be the answer. But you don't know which one, right? So you don't know what k you should use for the subarrays. Okay. So, but let's hold on to this thought. Okay.
But if you did like k slices of the array and then found the like the max of each one.
Okay, so what he's suggesting is, instead of breaking up the array into 2 pieces, you're suggesting basically breaking it up into k pieces. So one guess you might have is, okay, so if I break this array up into k pieces and look at the largest one, so if it so happened that the smallest k were all divided nicely between these pieces, then you can find, you can hope to find something like this. But all the small k could be in one piece, in which case you don't know what it was. So yeah, so these are all interesting thoughts, but I think it's very, very, very tricky to make such things work. Okay.
We can start with something like quick sort, but only half to the algorithm, and say we do one iteration of quick sort, and the pivot ends up in the first third.
Okay.
And we're looking for, say, like k is n over 5. Then we don't have to worry about the second half. We can just do the same sort of thing on the first part.
Okay, so let me unpack your answer because I don't know if everybody has seen quicksort before, but what he's saying is actually the right idea, right? Which is that suppose you end up. Actually, let me motivate it in a slightly different way because I think it's the exact same motivation. So I will do a slightly different. I'll ask a slightly different question. Okay. So what if you have a procedure that runs in time that is linear, okay? And I will call this an almost median procedure. Okay, so remember my goal is to find the kth smallest. But what I'm going to ask you to do is imagine that there's some procedure that takes linear time and returns an element of the array that is not too big and not too small. Okay, so as he was saying, let's say it is something like the n over 3th smallest element or something like that. Okay, so let me explain what this means. So I define an almost median. So define almost median as some element of the array that is We write it informally first, in the middle, right? In the middle of the sorted order. Okay, so and formally, let me not use K again. I forgot that I used K. Let me use R over it. This is the R smallest element. Let's say n by 4 less than R less than 3n. So is the definition of the almost median clear? It's some element of the array, and if you look at where this element lies in the sorted order, okay, so the array is A, right? So, and this is some unsorted array. A0, then almost median is one of these elements. It could be the first one, for example, or it could be the second one, something. But in the sorted order of A, which you don't know, this element is the R smallest, where R is something between n by 4 and 3n by 4. Okay. So I'm not telling you how you find this. Just saying that this is the definition of an almost median. Yeah.
R is unknown, right?
R is unknown. Yeah. All you know is that somehow there is some procedure that runs in O of n time, and it produces one of the elements of the array that's guaranteed to be something like this. Okay. So that's what I'm saying. And as you were saying, this is roughly the idea behind quicksort as well, that you're somehow able to find an element that's somewhat in the middle of the sorted array. We'll see that later when we do randomized sampling. But yeah, so this is the idea. Okay, so this is, and what I would like to say is, suppose there's a procedure like this, then life is good. Okay, so that's what I would like to first answer. So is the goal of this procedure clear? Okay, so the goal is just to find an almost median very quickly. Alright, so we'll come back to this in a minute, but let me tell you why once you find it, it's okay. Okay, and this is exactly what he was mentioning. So if you are able to find an element like this, so the claim is having access to an almost median allows us to reduce the problem size by a factor 3 by 4. So I write factor at least. What I intuitively mean is the factor less than 3 by 4. Okay, so then okay, so the new problem size will only be smaller than 3/4 n. That's what I mean. Okay. Now this is my claim. Okay, so suppose you have access to an almost median of the array. Then you can reduce the problem size to something smaller than 3n by 4. Okay. So do you guys see that? So what I'm saying is I give you some element that is somewhat in the middle of that. And what do I, yeah, after O and so can you see how you might be able to do this? Because your goal is to find the kth smallest integer. and I'm telling you, actually, if you forget about the almost median and stuff, suppose I actually gave you the middle element of this array. Like if I really gave you the middle element of this array. Now can you break the problem into something that is half the size? Yeah. Do you have your hand up? No. Okay. Okay, so let me pause for a bit, make you think a bit. Okay, so tell you, yeah.
We could make a new array with things that are always smaller than a natural element if we.
Right. So it's exactly like he also mentioned, which is, yeah, suppose I gave you the middle element. Now what you do is you go over the whole array, make a new array, which I will call B. So the procedure is consider the algorithm. Take the, let's call this almost median as some number x. For new array B by going over A and including only the elements that are less than or equal to x. Okay. So x was this element that I promised you was in the middle of the array in sorted order. Right? So how many elements will B have? So as defined, because x was the middle element, A will only have exactly n by 2 elements that are less than x, right? N by 2 plus minus 1. So let's ignore that for a bit. Okay. So if I gave you the middle element, then B is going to have exactly n by 2. But if I had an almost median, now how many elements can B have? Can it be much more? Yeah, now maybe you want to look back at our definition of almost median. Right? So I told you that x is not quite the middle element, but it's something that is, if you look at the sorted order of A, then x lies between n by 4 and 3n by 4. So it's somewhere over here. So if I look at the number of things less than x, I'm guaranteed that it is still significantly smaller than n. But how much can you guarantee? It's at most 3n by 4 by definition, right? Because x is an almost median. So you know that there are at most 3n by 4 elements that are less than x. And that is the main idea. Okay? So if you do this with an almost median, so then so since x is an almost median, B will have at most 3n by 4 elements. Yes.
Do you know that K is less than R, or are we assuming that we have to go through both parts of the array?
That's what we'll come to next. Okay. Yeah. So if you knew that, right. So what she's saying is, okay. So I found this new array B, which has more than 3n by 4 elements, and this is these are all the numbers in the array that are smaller than x. Right. So let's suppose that the size of B. So suppose size of B is some number, so it's R, let's say. Right? So suppose you know K is less than R, then what can you do? So if k is less than r, then what do we do now? So now how do you find the kth smallest element in the whole array? Like I would like, can you for example say that the kth smallest element in the whole array, could it so happen that it is not included in B? No, because B was the rth smallest element, and somehow, the x was the rth smallest element, and you've included everybody less than x in the array, okay, in this new array B. Okay. So in particular, it will have the kth smallest element, and more importantly, the kth smallest element in the whole array is also the kth smallest element in B. Okay, so k less than r, then the kth smallest element in the whole array of A is also of B. Okay. So this is what I claim. Now, does everyone agree? So this is just a simple observation based on the fact that x was the rth smallest element. I built an array which has everything smaller than it. Yeah.
I guess I'm a little confused in terms of, are we assuming that the kth smallest element is smaller than x?
Yes, that's equivalent to, that's equal to the same. Yes, I am assuming that x was the rth smallest element, and I am assuming that k is less than r, which is equivalent to assuming that the kth smallest element is also less than.
So if we get a almost median x, isn't that pretty much stating that your k smallest element must be somewhere below the median or almost median?
Yes, it's below the almost median.
So if I had a k that equals n, wouldn't that go in the top?
Right, so then it does not satisfy this property. Yeah, we'll come to that case next. Yeah. Right, so as she was saying, you have to consider both the cases. So this is the first case is if k is actually less than r. Okay. But in this case, I claim that you now have this nice situation that the kth smallest element of A is also the kth smallest element of B. Okay. So now what you can, at least in this case, you can just recurse on B and find the kth smallest element of B. And I claim this is nice because you've done O of n work apart from finding the almost median. So let's say I'm given that for free. So you've done O of n of work, and you've reduced, so you've constructed this array B, and you're recursing on a problem that is of size at most 3n by 4. Okay? So you've gone from problem size n to problem size 3n by 4 by doing only O of n work. And I claim that that is actually very good. That will end up with near linear time. But before we go there, let's look at what happens if k were more than r. So if k was more than r, then this is a simple exercise for you, so I won't do this. But you can think about it a little bit. Now you know that your kth smallest element is not in B. Okay? Because k is bigger than r. Actually, this can be if k is less than or equal to r, just to be precise. So if k is strictly more than r, then your answer will not be in B. Now what you do is construct a different array, which you call C, which has all the elements that are strictly bigger than x. Okay? And so I will give us so if k is more than r, okay, construct C with model. So again, this is all there in the notes that I sent you. So I'm just I'll give a rough idea. And in that C array, it turns out that you look for the r minus or k minus r smallest element. Okay, so now you don't look for the k smallest element. You look for the k minus r smallest element. If you want, you can think of a simple example where, let's say, r was something like n by 4, and your k was think of a simple example, r was n by 4, and let's say k was n. So you found some middle element. Now you build this new array which has elements bigger than that, and in that you now look for k minus n by 4. So yeah, so let's not go into that. So this is just a symmetric case. It's basically the opposite case of the one that we've said here. But the point is to note that if you had access to an almost median, by doing some effort, you could reduce to a problem of size that is 3n by 4 with an extra O of n of 4. Okay, so let me write down a summary observation. So what we've done is shown that the picture shows that if we have access to an almost median, then by doing can reduce okay. So this is a rough summary of the previous slide. Okay, so if you had access to an almost median, then by doing a little bit more work, you can reduce the problem of size which is less than 3n. Starting with the problem of size n. Okay. So yeah, so maybe before I show you how this translates to running time, maybe I will pause a little bit. You guys have questions about this case? The next case, you should go back and think about it because that will really help you understand this process. But if you have questions about this case, let me know. Yes? That's a good question. Yeah. So what I meant here is just run this whole algorithm recursively, which means you find almost median, do the same process there, even inside find almost median and so on. Yeah. So everywhere, actually, this was also a question in one of the Piazza, I think this morning, which I didn't get to answer yet, is that throughout when I say you recurse, you just use the exact same procedure.
So it's open at each level, but then you're only finding out like order time. I don't know how that adds up to n.
That is what we will see now. Yeah. So what we are saying, what he's asking is, okay, so how does this now translate to the overall running time? So let's write this down more formally. So what we're saying is T of n is smaller than or equal to O of n plus T of 3n by 4. There's also the time for the almost median that I am ignoring for now. Okay. So plus time for almost median which I have said is linear. So it's I'm ignoring because I'm including that as part of the first O of n. Okay, so that's why I'm ignoring it. All right, but if this were the recurrence, right? So I claim that this one solves to total of linear. And again, the easiest way to do this is by plug and chug. So let's do that. So for clarity, instead of O of n, let's write as some c times n, some constant n. Now, if you plug this in, so what you get is p of n less than equal to cn plus c times 3n by 4 plus p of 3/4 of 3n by 4. Right? If I replace n with 3n by 4 here, then this is what I would get, right? So I would have gotten c times 3n by 4, c of 3/4 of that number. Okay. Imagine replacing n here with 3n by 4. This is what I would. Now imagine replacing n here with this quantity. So this is what plug and chug means. So you get a cn, c times 3n by 4 plus c times that. Now I can see the pattern here. So it's 3 by 4 cubed times 10. So this is like 3 by 4 whole square times. Right? So this quantity is 3 by 4 whole square times n. The next time around I'll get 3 by 4 cubed times n, and so on. Yeah.
Should there be another t of 3 over 4 in the second?
Here?
Yeah.
No, so I have simplified this term. Maybe
Oh, I see.
It's right. So this term has split into these two terms. Okay. Because I've used the exact same equation, replacing n by 3n by 4 to do this. And this is how you do the plug and chug. Yeah.
When you said the T of 3n by 4, did you consider random problems within here?
Yes, you should do that technically speaking, but I'm saying that for now I'm including that into the c times n, because I've said that can be done in O of n. That's a good point. Okay, any other questions? Okay, so let's continue doing this. So now you can simplify this further. It turns out that you get something, if you do it r times, then you get cn plus c times 3 by 4 n plus c times 3 by 4 squared. R minus 1 times n plus p of okay. So this is the usual pattern matching that we did last time also, right? Like you see what if you did this expansion r times, then what you see that here you had 1 and 3 by 4 squared, and here there was a t with a 3 by 4 cubed. If you continue doing this, you will get the same thing. You have 3 by 4 to the r minus 1, and here you would get 3/4 to the r. So that's a general pattern that you observe. Now, so when can you plug in some known value of t? So as always, we know that t of 1 equals 1, right? That's a base case. So you would like to do this until this term became 1. So this term has to become 1. Okay, so we go on until P 4 and R times n becomes equal to 1. So earlier it was always halving or something, so it was very trivial to get the log n. But here you should be able to see this also. So for what r will 3/4 to the power of r times n be equal to 1? Okay, so yeah, so to solve anything like this, you just take logs on both sides, and if you really want to solve this, let's see. So this is equivalent to saying 4 by 3 to the power of r equals n, and which is equivalent to saying that r times log of 4/3 equals log n. It's like saying r equals log n divided by log 4/3. Log 4/3 is some constant, so this is still log n. So that's what this thing is. So this is good, right? So this is what you're going to set r to be if you wanted to get down to the base case. So now what will these terms add up to? Okay. So what are these terms, right? So I get P of less than equal to. Let me write this in a slightly different way. 1 plus So if I made r so that this thing was equal to 1, then this equation is basically this. It's exactly the same as this. Okay, so you got thing where r is equal to this quantity, and you have P of 1. Now what is this kind of a series? Can you give a simple bound on this? Yeah. So this is at most 4, because even if you had the sum to infinity, this is a geometrically decreasing sequence. Okay. So this is some fact that it's a simple fact. So the sum until infinity of something like 1 plus alpha square plus so on up to infinity is 1 by 1 minus alpha if alpha is less than 1 for any. So this is something that you guys should know. This is just sum of infinite geometric series. And now set alpha to 3/4. What you get is that the whole series is something like 1 by 1 minus 3/4, which turns out to be 4, like he's saying. And yeah, this is actually equal. So this whole thing is less than or equal to 4cn plus p of 1. In fact, it's strictly less because you're stopping something. And that's it, right? So this is the reason, even though your problem size dropped only by 3/4, like he was asking, you still get just a linear time. Okay, so that's the full analysis. Modulo the fact that you had somebody always giving you an almost mean. Okay, so any questions? So this is just a simple computation. So if you haven't followed the computation, just go back and look at it. It's just the geometric series that I've done. I've not done anything fancy here. Okay. So that's that. so the main question now is how do you come up with an almost median? Okay, so that's the next question. So given an array, how do you find an element that is somewhere in the middle portion? So any thoughts on how you do this? Suppose you had to do this in practice, how would you? Yeah.
We could just sample the array and choose median value from samples.
Yeah, so what he's suggesting is, if you suppose I wanted to find an element, so and this is, let's say I've sorted the array in increasing order. I want to find somebody that lies in the middle one half, right? That's all I'm saying. It lies between n by 4 and 3n by 4. That's my definition of an almost median. So I'm just saying that it lies in the middle n by 2 element. Now, even if I sampled one random element from the array, now the key thing to note is that sampling a random element from an unsorted array is the same as sampling a random element from a sorted array, because you're sampling a random element. Okay, so you could imagine conceptually that you're sampling from the sorted array, and then you can immediately answer, right? Like, what is the probability that if I sample one element from it, it falls in the middle half? So that would be exactly a half. Okay, so if I sampled, let's say, 100 elements, one of them is bound to be in this middle half with overwhelming probability, correct? Or let's say even 10 elements. 100 is an overkill probably, but so if you sample 10 elements, there's at least 0.999 probability that you found one person which is an almost median, right? So this is what you would do in practice. Sorry, practice. But we'll analyze algorithms like this when we do probabilistic algorithms. But for now, so in practice, this is very easy. Simple. You just pick a few random elements. And go with one that splits the array. And once you pick some element, in O of n time you can tell if this was an almost median or not, right? Because you just count how many are less than that number, and if it was less than n by 4, then you were unlucky, or more than 3n by 4, then you were unlucky. Otherwise, you found an almost. Okay, so this is how you do this in practice. So anyway, this is not what we will do. So, or you can do what he was saying, which is you pick, like, I don't know, 10 elements from this array, pick the median of those 10 elements. That you can do in constant time because there are only 10 elements, you can sort them and find the median. So that's another thing that will also work. Okay? And this is what you are doing in practice. But this is a probabilistic guarantee. Right? So there's some probability that you'll fail, and you'll always keep finding the n smallest element. So, yeah.
How do you know which one? Like if you pick 10 elements and one would be median probably.
Alright, actually anybody else want to answer that? Because I think I went over that too quickly. So suppose I gave you an element and asked you to tell me if it was almost median or not. Can you do it in like linear time?
Compared to two other elements, if it's between those, probably you're close.
Well, no, but you can even tell for sure, right? If I gave you enough n time, right? I gave you one element. Suppose I ask you, is this an almost median? And I ask you to do this in time n.
So unsorted array.
Yeah, it's an unsorted array. Yeah.
We can do our split into the arrays B and C, and if the sizes are appropriate for what we expect for an almost median, then it is.
Right, or simply speaking, you just go through the array once. Suppose the number you're given is x. Go through the whole array once. See, count how many are less than or equal to x. Now, if this number was an almost median, then that number would lie between n by 4 and 3n by 4. That's how you tell if an element is an almost median. So there's a simple linear time procedure that you can use today. So that's how you would do this. Yeah, but this is a probabilistic algorithm and it has some non-zero failure probability. Okay, so this is a good idea, but we need some more. We'll get to this sort of thing later in the course. Okay.
How drastically would the running time increase if you were to do essentially the same procedure you just described, but you search for using a binary search? So like you pick a lower and an upper bound and you bisect it to try to approach it.
Right, but the original array is unsorted, right?
Yes.
So you don't know how to
Okay,
do
so you wouldn't know whether or not it was in a subarray.
Exactly. Yeah, but that's a good question. You might think that maybe I can do something smart. Yeah.
Is it really important that we choose n over 4 and 3n over 4 as the bounds?
No, you can do n by 100. Yeah, you can do n by 100 and 99 n by 100.
Isn't it anything less than?
Any constant less than n would work. Yeah. Yeah. Actually, that's a good homework problem. Maybe I will include that. So, just seeing how the constants change if you're based on the lopsided. Yeah.
Yeah, like I'm pretty sure if you pick k to be n, you can actually approach n squared time. This all breaks down.
This will break down. Yes. Right. Yeah. So if you're terribly unlucky and you always ended up with the rightmost element, then this would basically be the same as selection sort.
Isn't this select?
Right. This is basically quick select. Yeah. Okay. All right, but this is the idea. Okay, so the way you should think about this algorithm is finding some clever way, having a clever way of computing this almost median. Okay, and so let me describe a deterministic procedure. That is one that does not involve any random guesses. That also achieves this. Okay, so I'm not going to go into the analysis of this algorithm, but it's a very popular algorithm and it's called the median of medians algorithm. And the idea here is that suppose your original array had length n. This is what you're assuming. And now you break this array up into pieces of length, some constant. Think of, so it turns out 5 is like a good number, but you can think of any constant. Any constant bigger than equal to 5. Okay, so just think of it as breaking up into groups of 5. And now you have n by 5 such groups. Right? And let's, for fun, just organize them, these groups of 5, in some vertical order. And what this procedure, the idea of this algorithm is to say that I'm going to look at the middle element of each of these tiny arrays. And these are tiny arrays, right? These are just size 5. Okay, so I can do this by brute force, and this is going to take constant time. I can find the median of the middle element of each of these arrays, and or imagine even like sorting these arrays, sort these small. That helps you think better. And now these are groups of 5, so I have n by 5 such groups. So just rewrite the original array. So now suppose I recursively use this procedure to find the median of these n by 5 numbers. Okay. So by the median I mean the middle element, right? So middle element in sorted order. Okay. So I use, let's say you use this procedure recursively to find the middle element of these n by 5 numbers, which are these middle numbers in these tiny arrays. Okay. So the claim is that that number would be an almost median. The claim is that let's give names to these, because I don't like talking about terms that are only there in pictures. Okay? So let's give some names to these things. So let's call these, let's call this one B1, this is B2, and this is Gn by 5. The point is that this is an n by 5 size array. And so the claim is that the median, i.e. the middle element, or to be precise, let's say n by 10 smallest element, of B is an almost median of A. Okay. This is a very clever algorithm, and if you see the names of the people who came up with it, it's you'll see why it's very clever. Okay, so these are all like the who's who of the 70s, 80s theory community. Okay, so and yeah, apparently subgroups of these people came up with the algorithm around the same time. Some of them were at Berkeley, some of them at Stanford, and they all joined together and wrote a paper. Okay, so that's the story of that, of how this algorithm came about. And the reason, actually, maybe I should spend a little bit of time about why people were interested in this problem. People have always been interested in the power of randomness. Okay, like suppose you can solve a problem quickly using some random bits. Like in this case, we've seen that if you're allowed to guess randomly, you have a high probability of solving this problem in linear time. And people asked, okay, so can you do it deterministically without actually sorting? Right? Can you do it deterministically also in just linear time? This is something that people always ask. And in fact, this Pratt, if you know, is one of the people who came up with a probabilistic algorithm for this problem of finding if a number is prime or not. Okay, so he's always been interested in this question of, oh, is randomness, does it give you some extra power in designing algorithms? Okay. And this question was kind of studied in the same light. It's like, I mean, it would be like a huge discovery if it were true that using randomness you can solve it in linear time, but without using it, you need n log n time. Then that would be a big thing. There is some intrinsic power that randomness gives you. So, but yeah, so this algorithm showed that that's not true. In fact, that's a big open question. We don't know of procedures of like very good problems where you can do it with randomness and you cannot do it without random. Okay. But anyway, so that's some philosophical reason why lots of people were interested in this problem. Because as such, it looks like a puzzle. Why so many big people work on it. So that's the That's the history behind this. Okay, and all right. So now back to the claim. Okay, so the claim is the n by 10th smallest element of P is an almost median of P. And the nicest way to see this is again by picture. Okay, so imagine I were to sort these blocks by the corresponding B element. So imagine sorting the B's. You don't actually do it, but just imagine sorting them. Okay? Then you would have a set of blocks. And the middle element that you found here is the median of this B. So let's call this number X. So this would be X. All these middle elements here all of these guys would be less than X because this was sorted. And all of these guys would be more than X. Okay? Now what I claim is that means that all of these elements, everybody in that left quarter, are all smaller than X. Why is that? Because these blocks, I said, were sorted. Right? So each of these blocks was sorted in increasing order. Okay? And so all of these elements would actually be smaller than or equal to X. Likewise, all of these elements would actually be bigger than or equal to X. Okay? Yeah.
So when you said it was sorted, B1 was sorted within itself, or was it sorted with respect to the B1?
So yeah, so these tiny arrays were all sorted within themselves. So this is smaller than this is smaller than this, and so on. Okay, and in this picture, the middle guys were sorted. This picture we are not actually computing it. I'm just drawing it for the purpose of analysis. Okay, so we are actually not doing this procedure. This is just it's like a thought experiment. Like suppose you were to arrange these blocks based on their middle element. Okay. Yeah.
So if suppose, for example, X was 5,
Mm-hmm.
and in one of the left arrays, I have the median as 2, but there were numbers bigger than 2 because it's the median within 3.
Yeah.
So then how would it be less than X? Like why are you doing this less than X?
So right. So that's a good question. So what she's asking is like a concrete example of this, right? So what she's saying is, if you had as X is here, so this is equal to 5. Now somebody here had 2 over here. Now the point is that this tiny array was sorted in itself. So everybody above 2 had to be less than 2. Right? So this would have been like 1 and 0 or something like that. So in particular, they would also be less than 5. Right? Because these guys would actually, everybody over here would actually be less than this element. And you know this element is less than this element. Okay? So that's the reason everybody on the left is actually less than X. Because these were sorted, so this would be less than this. And this is, of course, by assumption, this was less than X. So that's the point. So that's why you have everybody on that left quarter is. So let me pause a little bit here because it's a clever observation. Okay, and again, I'm not computing this sorted order. I'm just using it to prove this claim. So Alright, so let me assume this is true and then go on for now. So what I have shown is that if one were to recursively compute the median of this V, then you would have found an almost mean. Okay? So if you think about it, this then gives rise to the recurrence where you have T of n is the amount of time you need to run this procedure, which is now T of n by 5, right? Because now you have this n by 5 sized array on which you are recursively computing the median. So it's not constant like we hoped for, but it's turns out it's still not bad. Okay, so this you end up with Cn plus T of n by 5 plus T of 3n by 4. So this Cn and T of 3n by 4 are the same as before, just that for doing this you got a T of n by 5. Alright, so you had a question?
I think I just figured it out.
Awesome, okay. Alright, so this turns out to be the recurrence. So it's not as simple as before. It's not exactly Cn plus T of n 3n by 4. It's this plus this extra n by 5. But yeah, so now this is again exercise in either. Actually, if you try to do this as an exercise in plug and chug, then I would be happy if you can do it, but I think it will be very messy. Okay, so it turns out the easiest way to show this is some guess and prove. Guess that it is some C times n, and you just expand it out. C prime times n. It's not this C. Yeah. C prime, and it will all work out. Okay, so I think something like 20 times Cm would make it all work. So, alright, so I won't get into that, it's just a recurrence. Okay, so this ends up being O. Okay, and in fact, one easy thing that you can show is that actually, if you try to prove this recurrence, you'll realize why this algorithm was carefully constructed. Like, if my definition for almost median had been, 4n by 5, then this won't work. Okay, like he was asking, I think somebody asked this question that I could have defined almost median with like n by 5, 4n by 5. Right? So instead of n by 4, 3n by 4. Okay, it turns out for this recurrence it's important. If I had n by 5 plus p of 4n by 5, it turns out this is not linear anymore. This is n log n. Okay. So again, these kind of things you will see in your homework, which will be out this Friday. Okay, so any questions on this? So I have not shown you how to solve this recurrence, but you can prove that this is wrong. Okay. Alright, so we have a couple more minutes. So I don't want to start anything, but I wanted to end with some more examples of divide and conquer which we will not see, but these are like very well studied things that are all canonical in some sense examples of divide and conquer. Okay, so the first two you will find in the book chapter that I posted. Chapter of so this is the chapter that I posted. And this last one, yeah, I don't know if if it's very common, but it's another canonical example. So what is this matrix multiplication? If you've not seen it, this is very similar to the integer multiplication that we've seen. Okay. But now you want to, this is more powerful. So suppose you want to multiply two n by n matrices. So standard way of doing it takes time and cube. Okay, because you will multiply each row with each column. Computing every entry of the product takes n time. Standard way is like n cube. But if you try to do some divide and conquer like we did for for integer multiplication. Turns out that you can combine terms in some clever ways, and you end up with n to the power of log 7, which is something like n to the 2.7 something. Yeah, so it's 2.7 something. Just already quite a bit better than n cubed. So here again, there's a whole bunch of work about how you break it into further pieces. So some people suspect there are clever ways of breaking it up so you get n to the power of 2 plus epsilon. Okay, but we don't know the answer to that. Okay, so unlike the case of integer multiplication, we don't know how to do matrix multiplication in time that is significantly better than this. Okay, so the best known algorithm is something like n to the 2.36. So it's still quite a bit better than that 2.7, but it's not 2.01, for example. Like for multiplying numbers, you know n to the power of 1.01 is pretty easy. Okay, but here you don't know anything significantly better. Another canonical example is what's called fast Fourier transform. So I don't have time to go into that, but you can read about it in the book. It's very useful for like quantum computing and things like this as well. And graph partition is another standard example of divide and conquer. Like you want to do some manipulations on a graph. So you try to break the graph into pieces so that there are not that many edges going across. But then you can work with these pieces separately. So that's another standard divide and conquer technique. Okay. All right. So let's stop there.